fiber using the electrostatic forces. So what the fiber that we're getting over here, the fiber's diameter can be adjusted from micrometer to 100 nanometer or even few nanometer, depending upon what is the voltage that you're applying over here, the plus over here and the negative over here. And since this conducting polymer over here is conducting over here because of this electrostatic forces over here, what is going to happen depending upon the voltage? We can have this different diameters of this nano wires using of this conducting polymer over here. And in this process, what you do is this: a polymer solution is first forced out of this orifice to form a small droplets. And when you apply this very high electric field over here, what will happen is because of this high electric field, a charged solution jet is then extruded from this cone over here. And because of that, we have very thin fiber that is coming out of this from this needle over here. So these are the some of the ways where we can synthesize nanoparticles over here or nanowires over here. So also we can see over here the figure C where we make use of the LBL self-assembly of the gas sensors for the manufacturing process diagram. In the figure D, we can see that the 2D panel synthesis process diagram over here, where we make use of this aniline different doping agent over here, where we synthesize the nanoparticles over here, and where we make use of this synthesize this nanoparticle over here. So this is the figure G. The C shows the schematic of the fabrication process of the PPY framework over here. So it's a 3D structure over here. So, and this is the scanning electron microscope of the PVA PPY composite over here, which is impregnated with a boiling HCl aqueous solution and then freeze fried over here. And in the figure J, we can see over here the manufacturing process of this PVDF or P.NF sensors over here. And finally, at the figure K, we can see that the 3D nanostructure PVDF match fabricated to the electrospinning over here. So if you look at this image over here, it is the electrospun it's a P.dot nanofibers over here. And we can see over here, it's very highly porous structure over here. So what is the beauty of that? We can make use of this porous structure over here so that more number of gas molecules are absorbed on this gas surface and we can increase the sensitivity of this gas sensors over here. So when you make use of this conducting polymers over here, so we can see over here, look at these examples over here, the poly fibers over here. So depending upon what is the thickness of this what is the diameter of this nanofibers, depending upon this, the response of this gas is going to change over here. So over here, look at this diagram over here. We are making use of the different thickness of this Fermi film over here, and this is the response that we see for the different thickness of this film, how the response is going to change for the different gases over here. So over here, we need to optimize the thickness, we need to optimize the diameters of this for the detection of this gas, of this conducting polymer over here. The problem is this: the limitation associated with this polymer gas sensor is the selectivity challenges over here. The conducting polymers we know that there are several advantages, but also come with a certain limitations. And here are some common limitations associated with the polymer gas sensors. The first limitation is the selectivity changes over here. So achieving the high selectivity for the specific gases can be challenging for the polymer-based sensors over here. So what is the solution for that? To increase the selectivity of the gas sensors. So depending upon the metal or the metal oxide, which are sensitive to some specific gases, we make a nanocomposites of this with the conducting polymer, and we synthesize this nanocomposite to operate the sensors at the room temperature over here. The second problem with this is the temperature sensitivity. The sensitivity and the stability of this polymer-based sensor can be influenced by the temperature variation. So any changes in the operating temperature can affect the sensor performance, leading to an inaccuracy in the gas concentration. So mainly this gas sensors over here, when you're selecting the gas sensors over here, we need to be cautious over here, because even a slight variations of more than 10 degrees Celsius or 12 degrees Celsius can affect the accuracy of the samples over here. If you design a gas sensor which will operate, which is having certain sensitivity and accuracy at say at Mumbai or at Pune over here, it is going to have a certain value over here. But the same sensor, when you carry in some very hot area, Rajasthan or something, it is going to lose the sensitivity and its accuracy over here. So you should take care over here that all this factor is accountable when you're designing the gas sensors over here. The the second problem is this humidity. For all the sensors, as I described, that the humidity plays an important role. Even a slight change in the humidity is going to affect the accuracy of the samples over here. So the polymers which are made of this carbon chains over here can be sensitive to the humidity levels and the changes in the moisture content in the environment. So this sensitivity to humidity can lead to a false positivity or reduce the sensor performance over here. And the main factor with which the conducting polymer faces the main problem is with the stability over here. Since the polymers are made up of the chains of different carbon over here, over a period of time, what will happen over here? There will be degradation effect will come into picture, and because of that, the sensors performance is going to change. Overall, the sensitivity of the material is going to change. And all this factor, the response time and recovery time can be enhanced by making use of the different hybrid nanocomposite using the metals, metal oxide, and the CNT over here. So these are the solution. These are the solution of making use of. These are the solutions. These are the solutions where you make use of this nanocomposite with this conducting polymer over here. So we'll discuss about these three composites over here, where we make use of the composites of the metal and the conducting polymer. The second, we are going to make use of this metal oxide and a conducting polymer, and the third, we'll have an overview of this carbon nanotube with this conducting polymer. So the first composite that we are going to discuss is about this conducting polymer and a metal. So how can we make a nanocomposite? The first step is that to decorate the conducting polymer using this nanoparticle, or we can incorporate this nanoparticle within this conducting polymer during the in situ synthesis process or after the synthesis process. So what exactly is this? The surface modification of the sensing material with this metal nanoparticle has been an effective approach to improve the sensor performance over here. So what type of a nanoparticle you make use of this? You make use of the different nanoparticles such as silver, gold, palladium, platinum, copper, or nickel, because and it has been observed that when you decorate this metal nanoparticle, they increase the selectivity of this sensor, mainly because of the electronic sensitization and because of the absorption of a specific gases and a particular metal changes its work function during the charge distribution over here. So owing to this unique physical, chemical, and catalytic properties, metal nanoparticle assist in enhancing the sensing performance and the stability of this gas molecules. And what basically is this? When this make use of different nanoparticles over here, we provide some chemi absorption sites and all these things, and because of that, it shows good behavior to the different nanoparticles over here. To the first example, what you can see over here, we make use of this the copper nanoparticles, and we have made a nanocomposites of this copper nanoparticle with a polyaniline over here. And we see over here this nanocomposite can detect ammonia gases up to a ppm level at room temperature over here. So why copper nanoparticle over here? The first of all, this nanocomposite, because of this catalytic effect, will improve the response kinetics over here. And the why copper? Because the copper is considered because of the low cost catalyst, which helps in improving the conductivity, thermal stability, and it will help in the absorption and the deabsorption of the test gases on the senses of the thin film. So when you make a nanocomposite over here, always we see that the nanocomposite is properly made or not. So what you do is this. We have synthesized the copper nanocomposite over here, and we have done the mapping of this. When we have done the mapping of this sample over here, and we saw that when we do the elemental mapping of this copper over here, we can see that the uniform distribution of this copper using this nanocomposite over here. So we can see over here there is a good formation of this nanoparticle over here. And this nanocomposites over here, because of this catalytic effect over here, it's going to improve the sensor response over here. So what exactly is happening over here? As also we can see over here, this morphology of this sample is also play an important role in govern the response kinetic, because the surface roughness, the porosity, surface area to volume ratio, and the film thickness are the crucial parameters. And this we have optimized, and we saw that the concentration of about 0.13% of copper, atomic percent of copper, is best suitable for the sensor. So what you see over here, we can see the sensor response for the different ppm of the gases, and we can see over here as the concentration of the particle increases, the response increases, and after optimum concentration, that is about 0.13, it start decreasing. At high concentration, the decrease in the sensor response can be attributed to the shunting effect between the metal and the semiconductor, and the part of the sensor resistance that is shunted will not contribute to the response of the both absorption and the deabsorption process over here. So we can see over here, because after a certain point over here, it is going saturated over here. So in the next graph, what you see over here, the response of this body for the response of this body over here, we can see over here that the current is decreasing over here, and it can detect up to 2 ppm gases over here. Now, when you dope with this nanoparticle over here, we can see that it can detect up to 1 ppm level of gases. So what you do is this, depending upon the concentration of this gas, we pump into the stainless steel chamber and study the variations over here, and we observe 2 or 3 readings over here and try to find out what is the error in this sample over here. So this is how we make use of this nanocomposite to increase the sensitivity of this gas sensors over here. The next thing is this, it is sensitive to ammonia, but how it is sensitive to the other gases. So what you do is this, we perform a selectivity study over here, and we observe that it is more sensitive to the ammonia gases over here. We can see over here for at a concentration of 10 ppm over here, is around 55% over here. But whereas in the presence of the other gases, it is comparatively less, except this NO over here. So in this way, we do the different sensitivity study, the selectivity study, and accordingly we characterize or we develop this particular sensor over here. The next thing that we discuss is the room temperature NO2 gas sensor, which is prepared using the para-toluene sulfonic acid, which is doped with the silver polypyrrole nanocomposite. So what you exactly do is this, you make use of this silver nanoparticle and the polypyrrole nanocomposite over here. Why only silver? So if you look at the polypyrrole is a conducting polymer which is having a work function of about 4.12 eV, while silver has a higher work function, is about 4.26 eV. So it does not allow the formation of a Schottky barrier. So what will happen is this, because of this work function over here, it is going to form an ohmic contact. So because of that, it is going to provide a new absorption site, and because of that, we can see that the sensitivity is good over here. So what you do is this, we'll compare the results with this paper over here, where we make use of for detecting of this nitrogen dioxide gases. We observed that the sensitivity was about 64% and the recovery time was about 4,000 seconds over here, mainly because the structure was not so porous over here. So what we have done is this, we have synthesized this AgPPA nanocomposite using the in situ method over here, and then after that we have doped with an PTSA over here. So after doping, what will happen is this, it will create a porous structure over here, and because of this porous structure, the absorption and the deabsorption of gas molecule is going to increase, and because of that, we'll try to improve this recovery time over here. Because if suppose if the sensor is having a response time of about 4,000 seconds, it's not good for a sensor over here. So what you do is this, we synthesize first. We synthesize pure polypyrrole using the standard oxidative polymerization techniques, where we make use of this APS, and then we synthesize AgPPA nanocomposite without any external oxidant. So what you do is this, this is the first case where we synthesize pure polypyrrole using APS over here. This is the standard procedure for the polymerization of the polypyrrole over here. And this is the different way we'll make use of this in situ polymerization method in the presence of this nanoparticle over here. So how do you achieve this? So first, how do you synthesize this AgPPA nanocomposite? So what you done is this: you synthesize the silver nanoparticle in the colloidal form, and this is the reaction mechanism where we make use of this silver nitrate and the trisodium citrate to synthesize the silver nanoparticle, which is mainly in the colloidal form. And to that, what we did is this: we have added pyrrole over here. So because of this citrate ion over here, what is happening over here? It get polymerized, and because of that, the polymerization happen over here on the surrounding the silver nanoparticle over here. And after the synthesis of this AgPPA nanocomposite, what you do that is this: we dope with the PTS over here. So this is the procedure that we followed for the synthesis of this silver nanoparticle polypyrrole we doped with the PTS over here. So we can look at this result over there. Look at the result over here. For this polypyrrole over here, we can see over here the polypyrrole which was synthesized using the standard APS method, the polymerization method over here. It is having a good response time, but the recovery time is about around the 3000 second or the 4000 second over here. So what you do is this: because of this in situ polymerization over here, what will happen is this: we can see is this, when we vary the concentration of the silver nanoparticle over here, we saw that the maximum response was around of about 20% over here, or 20% over here. We saw that the maximum response of this 50 ppm level was forward for this concentration over here. Then we studied the variation of this concentration AgPPY for 20% of Ag. We saw that the sensor was able to detect a 5 ppm gas, as well as the sensor was able to detect about 120 ppm gas with the overall good sensitivity over here. So we can see over here the resistance was decreasing over here. So we saw that what is happening over here. So look at this image over here. This is the image of this pure silver nanoparticle over here. This is the image of this pure silver nanoparticle which was synthesized using the colloidal method over here. Then this is the image of the polypyrrole which was synthesized using the APS method over here. Then we can see over here, this is the image of this AgPPA nanocomposite over here. Now this we can see that the polypyrrole coated silver nanoparticles, the difference in the contrast clearly indicates that the silver nanoparticles are well dispersed in the polymer matrix, and there are minimum agglomeration over here, and which is the crucial role for the efficient transfer of the charges in the conduction process within the polymer matrix over here. So because of this, the nanoparticles are well dispersed over here. So there is no minimum agglomeration over here. Because of that, we have got a good response over here. And after that, after the doping with the PTSC over here, look at this image over here. They are comparatively well separated over here, and the structure is quite porous over here. Now look at this. Look at this readings over here. When it is doped with this PTSC over here, the response of this gas is for 50 ppm. The maximum response is we got about 15% over here. 15% doping of about 15% doping over here. We got a maximum response, and again we studied the variation for the different ppm of the gases, where you can see that overall the response increases over here. So this shows a comparatively study of about the sensor response as a function of the nitrogen dioxide in the presence of the 15% and in the presence of AgPPA and the PTSA doped AgPPA, where you can clearly see that the response of this gas is overall improved over here. Also, we look at this is a summary over here. This is the sensor response, where you can see that for when we have this PPY, the responses are about 30%. When it is doped with AgPPY, the response increases to about 35%. And when it is doped with the PTSA, again with some acid over here, PTSA AgPPY, the response increases to 50% over here. And when you look at the selectivity of this gas sensor over here, we can see over here it is this direction over here, that is in ammonia, but comparatively it was having good response to ammonium because we face difficulty in the ammonia gases over here. Also, we studied the stability of this gas sensor, and the sensor was stable to be initially the sensor response is about 50 percentage for about 50 ppm gases over here, and for a period of 30 days the sensor response decreased to about about 38% over here, so 33% over here. So we can see over here the after 15 days it shows degrading effect over here. So what exactly is happening over here? Because of this doping over here, it become porous structure over here, and this was confirmed by using the BET measurement over here. So using this BET measurement, we saw that the for PPY it is about 5, and for the PTSA dope it was about 16. So after doping with PTSA, the structure become more porous, and because of that, the absorption and the desorption of these gases increases rapidly over here. The next thing that we have synthesized is the metal oxide nanoparticle. Metal oxide nanoparticle when it is doped with conducting polymers over here. So what will happen over here? In contrast to the conducting polymer, metal oxide material have been shown great potential in gas sensing owing to its advantage of high sensitivity, fast response, and recovery connectivity. So, but the metal oxide gas sensors, they needs to be operated at a very high temperature, but they are selective to different gases over here. So why can't we make use of the advantages of this metal oxide nanoparticles in which to detect the different gases over here, and also make use of this the conducting polymer which operates at a room temperature, and we make an nanocomposite, so overall the response kinetic is going to increase over here. So the next step what we done is this: we have synthesized a nickel dope ZNO polyallyl nanocomposite, and we make use for the detection of this NO2 gas over here. So what exactly is happening over here is this. Look at this over graph over here. So this is the readings of this the zinc oxide nanorods, tin oxide pani is an Nano. Then we have the PPY, then tungsten oxide, and all these things. So we can see over here the sensor response over here. But all this, look at this. The zinc oxide nanorods operate at a temperature of over 200 degrees Celsius over here. But when it is stopped with the conducting polymer over here, it work on this room temperature over here. So what we done is this: when we studied the energy levels of the nickel, and we studied the energy levels of the zinc oxide over here, and we modified the material in such a way that we can when you make a composite of the zinc oxide nanoparticles and the polypyrrole composite, the HOMO and the LUMO levels of this conducting polymer matches with the energy levels of this oxide structure over here. So after engineering this the band gap over here, what we did is this: we studied the behavior of this nickel dope Zn over here in the air and in the presence of NO2 over here. So where you can clearly see that the presence of NO2, the depletion region is decreasing over here. So now look at this next graph over here. So this is the response of this the panic films in the presence of this NO2 gas over here. And after that, when we doped with the zinc oxide, the maximum response was about 20%, which was observed over here. Then after that, we studied the variation of this doped ZNO pani composite over here in the presence of the different ppm of gases, and where it was able to clearly sense of to 10 ppm of gases over here. But the problem is this: the response time and the recovery time was not so improved over here. So what he did is this: after optimizing the zinc oxide nanoparticle, after optimizing the concentration of the zinc oxide nanoparticle in the pani composite, what he did is this: we doped with the nickel. So we can see over here for different combinations, like for pani, what is the response? For zinc oxide pani, what is the response? And for the different doping, for 2%, 5%, 10%, 15%, we saw that the optimum concentration was about 10%, we got a maximum response. And this again, we studied the variation of here for different gases over here. And for 5 ppm, we can see that it was much more sensitive over here as compared to the other composites over here. So again, we saw the response time and the recovery time, where the response time and the recovery time improved a lot for this kind of gas sensors over here. So look at this. Look at this. This is the sensor response in the presence of the different pani, zinc oxide pani, and the nickel ZNO pani composite over here. So overall, when you design a material over here, and you make sure when it is doped properly in the presence of an acid over here, the overall response is going to increase over here. And this was again confirmed in the presence of this uh, the SEM images over here. Look at this over here. So this is the image of this nickel dope Z anode with 10% morphology over here, where you can see that the zinc oxide nanoparticles, which is doped with anode, was clearly visible over here. But when it is, this is the image of the pure party over here. This is the image of this zinc oxide, which is doped with party over here, and this is the composite over here, where you can see that the nickel dope Zedano Pani nano composite it shows a more porous structure over here. But the problem is this: when we try to measure the selectivity of this gas sensor over here, look at this. The sensor response was more or less same as this NO2 and NO over here. So again, the problem when you're designing a sensor, we don't know the mechanism what is involved for this what how the gas is going to interact and all this thing with the different molecules and how the response is going to behave for the different gases. This is still the major challenge that we face today over here. Okay, so this is the thing that we have done. When you look at the works of the other people over here, now look at this. Look at this image over here. The We can see over here this people over here, Farid et al. Demonstrated a room temperature ammonia sensors based upon the tungsten trioxide Pani composite. They grew Pani on the tungsten trioxide nanoplates via an in situ polymerization where they make use of the ultrasonic spray method over here. The tungsten trioxide Pani nanocomposite showed about 10 times higher response than the pure Pani. So you can see over here that when they made a composite of this tungsten trioxide over here, the response overall increases over here. So this enhanced sensing response was attributed to the modulation of the potential barrier at the interface of this N-type tungsten oxide, because we have this tungsten trioxide is an N-type material, whereas the pan is a P-type material over here. So when we have this interference over here, when it is the band gap, I'm not going into the detail of this about what is happening over here, but how they have selected the material in such a way that it matches with the Homer and the Luma levels of this conducting polymer over here. So we can see over here in the presence of the air, the depletion region is narrower over here, but in the presence of the ammonia over here, it is wider over here because what is happening over here? Look at this reaction over here. So this is happening because the adsorbed ammonia molecules consume holes. Ammonia molecules consume holes and protons from the amine groups of Pani, which results in the conversion of the emerald salt to emerald base. So because of this process, what is happening over here? The widening of the charge depletion region is happening over here, and hence the potential barriers of this tungsten trioxide Pani interface is going to increases, and because of that, the resistance is increasing over here in this case over here. The third example over here, what you see over here of this Narayan et al. Over here, where they synthesize this composites of Pani, where they synthesize the composites of Pani and ferric oxide over here. So what you do is this again they study the behavior of this energy levels of this Pani nanocomposites over here with the ferric oxide, and they modified this material and they tuned the band gap of this material over here. And for the different thickness of this composites over here, what they did is this different thickness of this composites over here, they measured the behavior of this nanoparticles over here. So and they observed that for a specific thickness only, the response was increasing. Why? Because they concluded that the thicker shell thickness reduces the ammonia diffusion. Because if the thickness of the shell is very large, so what is happening over here? Because of this the thicker shell, because the diffusion of an ammonia decreases, and because of that, it results in the low sensing response. Whereas the thinner Pani shell of the core shell structure cause lower residual hole and for ammonia interaction. So when you are designing the composite, we need to optimize for the thickness of this Pani nanocomposite with this nanoparticles over here. This is the one more example over here that we discuss over here. Now the next thing is this, where why not we make use of this metal nanoparticle. We decorate this metal nanoparticle with the zinc oxide nanorods and make a nanocomposite over here. So why we can make use of this metal oxide nanoparticle, metal oxide nanoparticle, the metal particle over here, and a nanocomposite. So what is the thing that we have planned over here? So what exactly is doing is this. So the morphology, as I said, that the morphology is going to play an important role for this for the designing of this gas sensors over here. So when you look at the morphology, size, and shape of the semiconductor metal oxide, among the various semiconductor metal oxide that we have, zinc oxide has several advantages over other metal oxides, such as high chemical and thermal stability, low cost, high electron mobility, making it an appropriate candidate for a gas sensing application. And also, studies suggest that the zinc oxide nanocrystals rods have 50 times higher electron mobility when compared with the zinc oxide nanocrystals over here. So what you're doing is this: you're making use of this zinc oxide nanocrystal rod over here, and in this case over here, since because of this high electron mobility over here, why not we can make use of this electron mobility of the zinc oxide nanocrystal to improve the sensor response over here. And after that, what we did is this: we synthesized first the zinc oxide nanorods over here. Then after that, we decorated them with a metal nanoparticle over here. So, so what you're doing is this: we have the hybrid nanostructure of the metal oxides and the nanocomposite, and then we decorate with the metal nanoparticle over here. So, what exactly is this? We have studied the energy levels of this zinc oxide and the Ag and this Ag over here. So it will results in the PN junction formation over here, and the addition of the zinc oxide in the addition of the silver in the zinc oxide will show to increase the sensitivity because of the new chemoabsorption site. So it is observed that this silver plays a very important role in creating a new absorption site. So we have utilized both the properties of these nanoparticles, that is the metal nanoparticles, to increase the chemoabsorption sites, and also we have used the important parameters of this zinc oxide nanoparticles over here for the creation of this hybrid nanostructure over here. So we have, in the first case, what you see over here, this is the response of the nanocomposite. But this is the response of this poly nanocomposite film for the different gases over here. And after that, what we did is this: we varied the concentration of the silver nanoparticle, varied the concentration of the zinc oxide nanoparticle in the nanocomposite, and we observed that for a concentration of about 10%, for 10%, the nanocomposite shows a good behavior over here. And so in that case, what we done is this: for this composite, that is approximately 10%, that is PZ10, that is for the PZ10, we studied that is a zinc oxide having concentration of 10% over here. We varied the variation from 5 ppm and 128 ppm, and studied the behavior of this the sensor for the different gases over here. And after that, what we did is this: we doped with the silver. We doped with the silver and studied the variations of this, and observe, and of that we saw that it shows a good response of over 2% over here. So after that, 2% doping is found to be most effective doping ratio for the ammonia resin. So, and after that, what we did is this: we studied the behavior of different. We studied the behavior for the different gases over here, and we saw that the overall sensitivity increased over here. So look at this next graph over here. So after the doping, you can see over here, this is the response of this sensor for about 75 ppm of an ammonia gas over here. We can look at this over here. The response type over here is drastically reduced when you compare with the PANI and the PZ10 over here. And after that, also you can see the recovery time also we can see the recovery time also have also increased a lot over here. But we can see over here, but the selectivity over here is having good, it's more selective to this ammonia gas over here, but whereas also it is having a small response to this H2S gas over here. But the question is this: why after 2% doping over here, why this the sensor response was decreasing over here? So for that reason, what we did is this: we studied the SEM image of all the sample over here. So look at the SEM image over here. So this is the SEM image of the zinc oxide nanoparticle, and this is the zinc oxide nanoparticle, which is 10%, which is doped with the silver nanoparticle of 2%, where you can see that the silver nanoparticles are quietly well dispersed within the zinc oxide nanoparticle over here. Then this is the PZ1018, where we have increased the concentration of the silver nanoparticle over here. So in this case, where you can see that the agglomeration forming over here, where you can see that the maximum agglomeration that is forming over here. So this is what you see the same image of the Pani. This is for the PZ10 and PZ10A2 over here. So look at this. When the final composite, that is PZ10A2 over here, we can see that the structure is well defined over here, and the structure is also porous, which are the requirement for this gas sensor over here. We can see that the more porous structure is often in this case over here, and because of that reason, the sensor was having good response to this ammonia gas over here. So this is the comparatively study of this PZ10A2 as compared to the results over here. So whereas in this case, the sensor response for the pure Pani for the other cases is about 3.86% over here, and for different response for the different nanocomposites over here, we can see that it is 5%, 21%. But in this work, we have achieved a sensor response of about 4%, and also the response time and the recovery time is improved a lot over here. And this is mainly because of this chemical absorption site attack created by the silver nanoparticle, and because of the zinc oxide nanorods which are formed during the synthesis process over here. So this are the procedure by which we synthesize these different nanoparticles over here. And next thing is this the upcoming field where the people are working on this because of this conducting polymer, the elasticity of this carbon change of this conducting elasticity of this carbon change of the conducting polymer also makes them highly suitable for the sensing layers of this integration into the flexible device over here. Also, we can see over here there is one paper by Narayan in which they have made use of this conducting polymers for the detection of these H2O gases and ammonia or nitrogen dioxide gases. And these sensors are fabricated using the screen printing or the inkjet printing over here. In this case, over here, we can clearly see that we can make use of this conducting monomer. Once the concentration of this is optimized, we can make use of this. We can make use of this nanoparticles, or we can make use of the conducting polymers to synthesize this flexible gases over here. The next slide, that what you see over here is the paper by Mandal over here, where they have synthesized again a flexible sensors where they have detected carbon dioxide over here, in which they were able to detect different gases over here for up to 500 ppm, and this flexible sensor we can see over here can be mounted on any device over here, and we can measure the response for the different gases over here. This is only possible because of making use of this thin conducting polymer over here. Also, what they did is this: they changed the diameter. They have applied pressure and say that a different pressure of how the material is going to behave, or how the sensor is going to behave for a different thickness over here, in which they also achieved a good response over here. Another peoples are working on the nanocomposites, a hybrid nanocomposite based upon this graphene and this conducting polymer, mainly because the graphene is having a high surface to volume ratios, and also graphene exhibit excellent electron mobility, larger surface area, high carrier density, and low resistivity of room temperature. Because of all this effect, they make use of this graphene CNT over here for this detection of this nanocomposites over here. I don't have any expertise in this the synthesis of the graphene or the carbon nanotube over here, but also this is an upcoming field where the people make use of this nanocomposite for the detection of these various gases. Of all the gases that we saw over here, of gas sensor that we saw over here, whether it is a zinc oxide sensor over here, or a conducting polymer nanocomposite sensors over here, or a CNT sensors over here, all the sensors mainly face problem with only one thing, that is the humidity over here. To overcome this humidity problems over here, what we do is this: we can have conducting polymers with a deeper homo levels, that is about 5.2 eV. We can functionalize this conducting polymer using this hydrophobic phenyl or the naphthalene ring, and you can improve this the effect from the humidity. And also you can make use of the additive like a cross-linker and all this thing to reduce the humidity effect of this gas sensor. Because when you try to reduce the humidity effect of this conducting polymer, you compromise on the selectivity or the sensitivity of the gas sensor. So once we need to properly balance between the conducting poly, once you have to properly balance between the both the thing, the humidity effect and the sensitivity effect. Once it is optimized, we can possibly have a good gas sensor over here. Now, what are the major challenges of this conducting polymer gas sensors over here? This conducting polymer gas sensor, as of now, also face problem with the conductors, because there are some conducting polymers in which when a slight variations on the temperature can the conductance of this material is going to change. So in that case, we need to select the materials, or when you design the nano composite where the material is not going to change its conductivity when a small variation in the temperature over here. So the main challenge is that we design a composite or fabricate a conducting polymer where the conductivity is not going to change with a small variation in the temperature over here. And also the main problem is the with this humidity. This humidity is very crucial factor over here. So we need to make use of the different enclosure where you can improve the humidity of this gas sensor over here. And also the main challenges that we face using this connecting polymer gas sensor is the stability and the selectivity. As in the previous slide over here, you can see that these sensors are not stable more than 30 days, 40 days, or 45 days. So, but if we have a sensor that is installed, or anyone purchases this sensor, it cannot have a stability of more than 40 days. No one will buy the sensor. So one major challenges of this conducting polymer gas sensor is this to improve the stability of these gas sensors. And also the last part that we saw is the selectivity of this gas sensor. So as all the previous slide, what we saw is that you see the different gases over here. It is not so sensitive to only that target gases, but also it is sensitive to the other gases over here. So when you design a gas sensors, make sure that you functionalize the material, you functionalize the conducting polymer, you functionalized or change the parameters of this nanoparticles over here, so that it is specifically selectively to a specific gases over here. If it is not, then the selectivity is a major challenge. This selectivity issue can be mainly solved by using a multi-array sensors over here. So what you do is this: you take a substrate where you mount with the various sensors, the one which is sensitive to 1 or 2, the another sensor which is sensitive to ammonia, the other sensor which is sensitive to H2S. So what you do is this: we have a multi-array of sensor that is mounted on a specific substrate, and we make use of the different array of the sensors and couple using it as some algorithm and study the behavior over here, and you can differentiate for the different gases over here. So this is the solution for the selectivity of this gases over here. So these are the future aspects or future perspectives of this problem. All the gas sensors that we saw over here, the main problem is this: that all the sensors are all tested in the labs, but when the sensors in the complex environment over here in the actual field, they deteriorate because humidity, they deteriorate because of moisture. So in this case, we need to also, once it is optimized, also we need to work on this factor to improve the on the presence of the humidity, moisture. The also in all the things that we have discussed, the mechanisms in the present literature over here, except for the specific gases like an NO2, ammonia, the mechanism is well defined over here. But what about the mechanisms of the gases in the presence of the other gases? How it is going to interact? Once you have a better understanding of the mechanism of this gases, we can clearly design a good sensors over here. And the big problem is just the reproducibility. This conducting polymers are in such a way that when you synthesize this conducting polymer at the lab, even a small variation in the temperature, pressure, or any other factor, it will not produce a reproducible results over here. So all this thing needs to be optimized properly, and accordingly the sensors have to be fabricated accordingly. So these are the main challenges that we are going to many people are facing while the synthesis of this in a particular way. With this, I'll end the topic over here. Thank you very much. Thank you for your attention. Thanks a lot, everyone. Over to you, Vivek sir. Thank you. Okay. Sedano and polyaniline nanocomposite. Okay. Sedano. You any specific paper you're asking for, or any what exactly which paper you should refer and all this thing?
Sir, this paper link is also okay, which you showed for same time.
Okay. Zinc oxide pani.
Yes, sir.
Okay, just a minute. I'll share the screen. Just a minute. You're talking about which zinc oxide pani, no? This is the paper for the zinc oxide nanoparticle PPT
Uh,
sensor.
no, not sir. This room temperature ammonia sensor based copper nanoparticle
Yes.
intercalated.
Okay. 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 This one. You're talking about this one. Yeah, this one, no?
Yes, sir. Just a
Yes.
minute, sir.
अगर आपकी भी घर में बनती है पनीर की सब्जियां तो जरा
I know it's lunch time. So you can type in a Google Scholar and this paper you can just go through. And if you want a full paper of that, you can contact me.
Okay, sir. Your contact
Okay.
number, sir?
It's Narayan, Narayan, Narayan 3006 at gmail.com. It is also available in this paper also. You can refer. This paper also you can find the links.
Okay, sir. Thank you.
Am I audible?
Hello. May.
Yeah.
Yeah, sir. P dot poly 3,4-ethylene dioxythiophene. The surfactant or dispersion medium. Generally, the PSS most of the paper.
Yeah, P.dot PSS. Yeah.
Yeah. Then any other dispersion medium that if if you
So
want to go for P dot.
no, I'll go for P.dot PSS because the energy levels, when you look at energy levels of both this thing, so the best thing is that the P.dot PSS is over here. The one thing you can optimize on the synthesis procedure over here. So mainly, so when it is you're planning to spin coat or what exactly you're planning for?
That is, in terms of suppose we want to make nano composites by using the P dot and metal oxide,
Okay. So
then
you're going to spin coat or you're going to do in situ
uh,
polymerization?
in situ polymerization. That
Okay,
means,
in situ polymerization. So what
yeah.
you do is that the timing during the polarization is very crucial over here, and also the how do you are going to in situ polymerize? How do you in situ polymerize exactly in your
That
case?
means by using the chemical synthesis refluxing
Yeah,
method.
yeah, but what is the procedure? Means simply you're going to uh, drop means
Uh,
कहाँ पर polymerize put a कहाँ पर polymerize करने वाला मतलब glass slide में या किधर?
no, sir. Suppose I want to make a chemical synthesis by
Uh-huh.
using simple refluxing method at particular temperature.
Okay.
Can I go with other dispersion medium or PSS we have to use?
PSS is good according to me. I'll say
Okay,
that according to me that please don't go further. We thought PSS is the best
okay,
as per our knowledge.
okay. Thank you, sir. Thank you.
Okay. And one more thing you can do is this. You can also because she's an expert on this, can contact Shilpa Jain because
Shilpa
the chemistry.
Jain.
Yeah, the chemistry part she looks out.
Can
Shilpa.
I get her email ID here?
Yes, Shilpa Jain. Just ping me. I'll message her email ID. Okay, because
Um,
I'm a physicist, and to be frank, I'm,
yeah,
a,
yeah, yeah.
but when you synthesize this for this solar cells, we are also looking out for this organic solar cells. Try to synthesize this organic solar cells and all these things. When we are fabricated a P.PSS, a thin layer of a P.PSS on the surface of the CTO. So the main thing that we observed is that the P.PSS is the good thing. So where you make use of this spin coating technique for this thin film on the ITO substrate over here.
Okay. Can I contact her then later on?
Yes. The email ID, no?
Huh?
You mail me. I'll send her email ID.
Yeah, please,
Okay. It's
please tell me.
I'll type my email ID in my chat box.
Okay, okay, sir. Okay,
Yes.
fine.
Mobile number, please note, sir. Because if suppose if I'm in the lecture, I'll not maybe answer. If you're in the mail, I can revert it back to you. I'll revert it back to you, please. Yes. It's my personal email ID. I have typed in my channels.
Okay, sir. Thank you.
Yes. Yeah. Okay. 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 Uh-huh. Okay. Okay. Uh, okay. So the thing is this: if you are synthesizing this on a substrate, if you're looking out for the morphology, First, look at the roughness value over here. Well, in the optical case, in the optical microscope, what is the roughness value over here that you get? And after that, what you do is this: to start up with, before going on to the temp, I'll suggest that you can make use of this atomic force microscope (AFM), and you can see the overall morphology of that particular sample over here. And when it satisfies your data, or when you see that it is optimized properly over here, then we go for the TEM analysis. And this TEM analysis, what you can do is this. If it is a solid sample over here, to be frank, the sample preparation is it's a huge task over here. So it has to be polished properly over here to few micron range over here. Then after it can be loaded into the TEM sample over here. So what I suggest is that you go for the yes. You can go for an AFM. You can go for an AFM. Um, yes, yes. Okay. In TEM, but you're looking at a feature which is limited to what range? Means we can tell me what is the dimension for that? Dimension, if it is 10 nanometer, 200 nanometer, or it is 50 nanometer. You're looking at for which dimensions? Because 10 nanometer. Have you done your characterization for your SEM? SEM? Okay. 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 Yeah. Uh, uh, okay. No, if you, it is transmission TEM or the tunneling electron microscopy you're telling, or STM. You can also go for STM also, because the sample preparations now STM is also. Yes, yes. So, to be frank, I need to do some literature on that particular, because I don't have expertise in that field. But what I suggest is this: you better go for an first AFM first, and then if you see the results are good, then you go for an STM. Then after that, you go for a TEM analysis over here. Okay, and we can discuss this after this with detail, means what exactly, because I don't have an expertise in that particular field over here, or on that what the samples that you're talking about, because I don't have much knowledge of that specific. Okay. Yes, yes. But the thing is yes, yes. But, what I'm trying to say is that I don't have expertise in that particular ceramic or that domain structure that you're saying now. Okay, that I don't have, but I can. You can have a discussion on that, sir.
Hello, sir.
Yes, sir, Kiran, sir.
Uh, if I want to do some characterization, what types of instruments are available with you, sir? If
As of now, at over here where I work over here, we have the basic UV and IR over here, and that is also with the collaboration over here. But the thing is, that there is a center at Mumbai University over here, Center for Nanoscience and Nanotechnology. They do
okay,
the different characterization on a chargeable basis, and also at SEF, that is IIT SEF.
yeah,
So
yeah,
what kind of characterization that you want, you can opt for that. But again, that is on chargeable basis. Okay. The problem
okay,
is this. The problem is that as of now, I am associated with some associated with engineering college over here, and we have different it is related to IoT and all this thing. But the
Yeah.
dedicated research instrument like TEM, SEM, AFM, XRD are available in the University of Mumbai. Then we have at IIT, and where we can characterize your samples.
Okay. 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 Okay.
Okay, and all the what are the details, what are the charges, and all this thing there in the website. And
Yes. Yes. Sure. Sure. I will
no,
check.
sorry, I'm not in direct in I have one or two that is on collaboration over there, but not in our institute. We don't have any this TM, SEM, and all this thing.
Okay, sir. No problem. Thank you. Thank you.
Thank you. Mumbai University, there is Center for Nanoscience and Nanotechnology. There they have the AFM available, and also I think in Pune University also there is some there are available there are AFMs. Piezoelectric microscope. No idea, sir. No idea, sir. Piezoelectric microscope, I don't know where it is. AFM, what is PFM? So I don't have any detailed idea on this. I've not worked with this PFM, but I worked with it. Yes, yes. I don't have this AFM. The thing is this all this work that you saw over here, it was we did a collaboration with the BRC people and all this thing. So so in that case, they have the dedicated center over here, but the access is very difficult over there to get into all this instruments and all this thing. Yes, yes. But all this thing that what you work that we saw over here was during the PhD time when I was a PhD student over here, and after PhD the postdoctoral research and all this thing. But as of now, I don't have any direct access because I also need a permission to visit that particular lab and all. Yes, and it's a very big procedure. Thank you, thank you. Thank you. Thank you, sir. Thanks a lot. Thanks a lot, everyone. Thank you. Thank you very much.